An industrial robot at rest appears to be a single, solid piece of machinery. In reality, this mechanical frame serves as the housing for an integrated architecture specifically designed to bridge the gap between digital logic and physical tasks. To operate independently, this system must solve a massive engineering problem. It has to map the absolute logic of digital processing onto the chaotic, unpredictable reality of the physical world. The architecture divides into 3 nodes: perception, computation, and action. Perception uses sensors to gather raw environmental data. Computation uses controllers to process data and make decisions. Action uses actuators to translate decisions into physical movement. Without a persistent connection, these components remain disconnected hardware. True autonomy emerges when the 3 nodes link into a continuous loop, allowing the machine to perceive, decide, and act as a unified system. To understand how a robot actually functions, we have to systematically dismantle this architecture, component by component, before we can observe how they dynamically interact. The first step in achieving autonomy is data acquisition. The robot must continuously translate raw physical states into quantifiable digital signals. This diagram shows proximity sensors capturing data. The robot emits wave patterns that detect immediate boundaries, calculating distance to avoid collisions. For complex navigation, vision sensors use camera arrays to capture high-density data, mapping the surrounding environment in detailed resolution. Once raw visual data is captured, computer vision algorithms process the pixels to identify specific targets, like geometric objects on an assembly line or anatomical landmarks during robotic surgery. Physical interaction requires touch sensors. Pressure and tactile feedback are strictly required for tasks involving delicate physical manipulation, ensuring the robot applies enough force to hold an object without crushing it. Beyond spatial awareness, environmental sensors measure ambient conditions. In agricultural robotics, monitoring exact temperature, light, and humidity levels is essential for optimizing plant growth. Without this constant, high-fidelity sensory data acquisition, the robot remains blind, deaf, and completely isolated from its environment. In this diagram of a robotic joint, we move from digital perception to physical output. Actuators are the mechanisms responsible for taking electrical signals from the controller and converting them into actual mechanical force. Electric motors serve as the standard baseline. DC motors provide continuous rotation, while stepper and servo motors are utilized when the machine requires precise micro-positioning. When industrial assembly lines demand rapid, high-force movements, engineers rely on pneumatic actuators, which use compressed air to punch or press materials with immediate kinetic energy. Hydraulic systems utilize fluid pressure instead of air. Fluid dynamics create massive payload strength, making hydraulics the primary choice for heavy construction and material handling. More specialized tasks require non-traditional mechanisms, like shape memory alloys. These specialized metals change their physical structure directly in response to temperature variations. Because they are lightweight and compact, they offer an effective alternative for soft robotics and internal medical devices. Ultimately, actuators dictate the absolute physical limits of a robot's interaction with the world. They bottleneck the system. Even the most intelligent programming cannot exceed the mechanical capabilities of the hardware. This visualization maps the central controller. It is the processing brain perfectly positioned between the incoming stream of sensor data on the left and the outgoing mechanical commands on the right. The simplest version of this hardware is a microcontroller. These compact devices provide foundational data processing, suited for basic automated systems or remote-controlled vehicles. Scaling up to manufacturing, industrial robots rely on programmable logic controllers, or PLCs. These are heavily ruggedized units capable of handling multiple inputs and outputs simultaneously in harsh factory conditions. At the highest tier are computer-based controllers. Autonomous vehicles and robotic surgical suites require massive processing power to run complex machine learning algorithms and interpret high-density sensor arrays in real time. Regardless of the tier, the controller's singular purpose remains exactly the same: to constantly translate arrays of environmental data into perfectly coordinated mechanical choreography. A system that receives a command and executes it blindly is an open-loop system. True robotic autonomy requires a closed-loop system, where the machine continuously checks its own physical work. This wireframe demonstrates the closed loop. First, the controller issues a calculated command to the actuator, setting an intended path to grasp a target. Physical actuators will invariably deviate slightly from the ideal command due to payload weight, friction, or resistance. The perception sensors instantly detect this physical deviation, measuring the exact distance between the arm's actual position and the intended target. This physical gap is quantified as an error signal, which is immediately transmitted backward into the controller. The controller recalculates its kinematics based on this precise error and sends a new corrective command down to the actuator. This continuous loop of execution, error detection, and correction happens microsecond by microsecond, ensuring millimeter precision during complex tasks. This real-time cycle, the feedback loop, is the measurable engine that transforms blind mechanical movement into actual autonomy. While the feedback loop is theoretically perfect on a whiteboard, real-world deployment stress tests these hardware components, exposing severe physical limits. Sensors have specific environmental vulnerabilities. Sudden drops in lighting or unexpected physical occlusions can blind a vision sensor, cutting off the data supply to the controller. Actuators suffer from physical degradation. Electric motors overheat when operated continuously under high loads, and pneumatic systems lose massive amounts of efficiency if tiny air leaks develop in the lines. The controller itself becomes a bottleneck. Processing vast amounts of high-resolution sensor data while simultaneously calculating real-time kinematics requires immense, power-hungry computing overhead. Ensuring compatibility is the paramount challenge in component design. Engineers must force widely varying physical tolerances and digital bandwidths to synchronize seamlessly. Overcoming these hardware bottlenecks requires an evolution in how robotic architecture is distributed. This diagram illustrates the next generation of robotic architecture. System design is shifting away from a single, centralized processing core toward a framework of distributed complexity. Hardware developers are building smart sensors. By embedding local artificial intelligence directly into the camera or proximity device, raw data can be processed at the exact point of acquisition. On the mechanical side, soft actuators are replacing rigid industrial metals. These highly flexible materials allow for passive, biological-style adaptation. Instead of relying solely on complex calculations to grasp an odd shape, the material itself conforms to unpredictable environments, making it highly effective for delicate surgeries or search and rescue operations. Tying this together is the concept of edge computing, pushing critical processing power out of remote data centers and as close to the physical sensors and actuators as possible. By eliminating the latency of waiting for a remote server, edge computing enables the instantaneous, zero-delay decisions required for an autonomous vehicle to survive a highway at high speeds. Robotic capability scales not with the power of individual motors or cameras, but with the efficiency of the information flow between perception, computation, and action.